Hi folks, and welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to find differentials and compare differentials to the differences in function values. For those of you in my Calc 1 section, the intention here is to help you with homework problems in section 3.9 from in the 29 through 33 region. So we're going to take a look at number 30 here, where our function is 2x squared plus 4x minus 3, and I'm just going to take a moment and pause this. All right, there, I'm back. All right, so when you look at problems 29, 31, 33, when you read all of it, you might get kind of lost. When they talk about delta f, they're just talking about the difference in the function value here. So when we look at delta f here, what we need to know is we need to know the function at x equals -1. We need the function at x equals -0.9. Here's where I'm getting that from. We're talking about starting at -1, and our change in x, our dx, is positive 0.1, so we're going to be moving to the right by an amount 0.1. That will put us at -0.9. This one right here is equal to 2 times 1 for this term. This is going to become a -4 when we put a -1 right here, and then -3. Which is, let's see, this is -2 minus 3, this is -5. F of -0.9 is going to be 2 times -0.9 squared plus 4 times a -0.9 minus 3. I'm going to take a moment here, I got to run that on a calculator here. Okay, let's see. And I get -4.98 out of that. Okay. So delta y, or delta f, the change in f is going to be this guy minus this guy. So that's 0.02. Okay. Done. Okay, now let's talk about df. Now df stands for differential in f. And if we take this function and we calculate its derivative, remember this is like y equals, then dy dx, or we could say df dx, is equal to 4x plus 4. I'm getting that from differentiating this. Remember that the derivative of the constant is 0. Therefore, df is equal to 4x plus 4 times dx. In this example, that's going to be 4 times -1 plus 4. Now what we're doing is we're using, technically this is a delta x. I don't know why the book labels it dx, they really shouldn't. But what we're doing is we're approximating dx with this 0.1. Remember, dx is technically an infinitely small value, but what we're doing is we're using 0.1 to approximate dx. I'm going to go ahead and take a look at this. So this is going to be a -4 plus 4. That gets basically 0 out of that, which is fine. That means that the tangent line is pretty close to horizontal at that point. Actually, to tell you the truth, looking at this, it is horizontal, because df dx, remember, would give you slope of the tangent line at that point, and when you put a -1 here, you get a 0 out of it. So that's fine. And then the very last question was delta f minus df, an absolute value just to give us a positive quantity. So in this example, that's going to be 0.02 minus 0, absolute valued, if I write it all out, which is 0.02. Now, this is how you work problems 29, 31, and 33. The only difference is, my guess is, when you do 29 or 31 or 33, this probably won't be a 0. So what'll happen is, this value won't actually equal the delta f. This was the reason that this ended up equaling this, which is the same as delta f. That's only because the linearization of this function at this point is horizontal. In all the other examples, you'll get a value here that's different than the delta f. So anyway, I think that video should help you with 29, 31, 33. I'm going to stop that now and make another one talking about differentials for changes.